Automotive headlights have been on the road for nearly 135 years, but surprisingly, driving at night is still very dangerous. Today's headlights are bright, energy efficient, and even adaptively illuminate the road. But even the best ones are not generally for performing multiple tasks, and they typically require mechanical parts. We have developed a headlight with a single hardware configuration that can be programmed to adapt to any road environment. The key component of our design is a spatial light modulator, such as a DMD chip, commonly found in DLP projectors. The benefit of using a spatial light modulator is that a single beam from a light source can be divided into a million smaller beams, each of which can be controlled to react to the environment. The spatial light modulator is optically co-located with a camera that senses and captures images in front of the vehicle. The images are analyzed with a processor that also controls the spatial light modulator to appropriately illuminate the road environment. In order to be useful at highway speeds, we determined that the headlight needs to react within 2 milliseconds of acquiring an image. A high-speed spatial light modulator was built by combining a custom DMD board and the chip with the optics and the light source of an off-the-shelf DLP projector. The result is a spatial light modulator capable of display rates of over 1000 Hz. The prototype is a little bulky, so suction cups are used to mount the prototype on the hood of a pickup truck for road testing. We demonstrate the versatility of the headlight by first addressing one of the biggest problems while driving on the road: the glare problem. The solution to this problem is straightforward, due to the high spatiotemporal resolution of our prototype. After detecting oncoming vehicles by their headlights, only the light rays directed toward other drivers are disabled. This works for any number of vehicles in any number of lanes on the road. This should look familiar to anyone that has been blinded by headlights. The anti-glare feature of this prototype is disabled to emulate the glare typically seen from standard headlights. When our system's anti-glare function is enabled, the difference is very dramatic. The oncoming driver is no longer blinded, and the vehicle and the road environment become more visible. Now, how does it look to the driver equipped with the headlight prototype? Because the prototype has unprecedented resolution over space and time, there is little perceptible difference to the driver, even with 3 oncoming vehicles in the other lane. So with the programmable headlight, drivers can use the brightest headlights available, or always keep their high beams on without losing too much light. This is a stark contrast to LED-based anti-glare headlights. Another problem that our headlight can address is poor visibility in the snow. Driving at night during a snowstorm is a nightmare. Snowflakes appear as bright flickering streaks and are very distracting. The problem is mainly caused by light from our own headlights reflecting off the snowflakes back to our eye. The solution to this problem is very simple with our headlight. By avoiding illumination of the snowflakes, in other words, streaming light in between the snowflakes, the visibility of the snowflakes will be reduced. This might seem like a crazy idea, but preliminary experiments with artificial snow demonstrate that it is technically feasible while significantly improving visibility with little loss in light. The current prototype is 10 times faster than our previous prototype, with much better performance, bringing this technology closer to reality. Improving visibility of the driving lane is also possible due to the flexibility of the headlight design. Increased lane contrast can be created by illuminating the driver's lane more brightly than the adjacent lane. Drivers can more easily follow their lane on poorly lit, dark roads. This application is even more beneficial on roads with worn, absent, or snow-covered lane markings. In the same way that lane visibility can be improved, obstacles on the road can be made more visible as well. Our prototype can be used as an accessory to standard headlights to provide an early visual warning of obstacles. For example, it can potentially be used to spotlight deer, pedestrians, and signs. In one example, we demonstrated that bicyclists on the road can be spotlighted. Bicycles are detected by their reflectors, then the headlight illuminates in the direction of the bicycle and the bicycle itself. The current prototype can track objects traveling 80 kilometers per hour, crossing at a distance of 5 meters in front of the vehicle. To summarize, we have built a prototype of a new headlight with a single hardware configuration that can be programmed to perform a variety of tasks. We have demonstrated 4 example applications, but the possibilities are endless. And we strongly believe that once our system is installed in a vehicle, it can have a significant impact towards saving lives.